All right, welcome back. Module number 1, lesson number 3, we're going to talk about really just a basic chapter. Certainly what we're going to see in this chapter could be a whole day's discussion in and of itself, talking about MPLS and DMVPN and whatnot. But that's not really the point of this chapter in this particular case. Our goal here is just to introduce you guys to some concepts. We're going to see more about this type of stuff and talk more about these types of concepts when we get into the internet connectivity module, which is module number 6 later on down the road. But this is the lesson number 3, which is connecting remote locations with your headquarters location. And there's two ways that we can do this. We can either do this by utilizing something called a traditional VPN, like leased lines or frame relay, or we can use newer VPN technologies, service provider managed VPN technologies like multi-protocol label switching, or DMVPN, dynamic multipoint VPN technology. All right. Both of these solutions are very flexible. They offer a lot of connectivity options, a lot of different connectivity options, and just in general, just provide better connectivity services that we didn't traditionally see when we were dealing with frame relay, ATM, X25, and so on. So we're going to take a look at options for connecting our branch offices and our remote locations, whether we decide to use a service provider managed VPN or whether we're going to use an enterprise managed VPN. We'll talk about the interaction of routing protocols with respect to VPN, specifically MPLS VPN, because we can deploy MPLS VPNs in two different formats. We can deploy it as a layer 2 MPLS VPN, or we can deploy it as a layer 3 MPLS VPN. We'll talk about the use of generic route encapsulation, what that does for us. We'll talk about DMVPNs, and then finally we'll talk about Multipoint GRE and the next top resolution protocol. And then we'll wrap up this chapter or this lesson by talking about the role of IPsec in our DMVPN architecture. With regard to options, the options that we have for interconnecting our locations, there are essentially two different models that we can deal with. We can deal with a model that's called a service provider managed VPN, where the service provider participates in actually providing VPN connectivity. They're either doing that at layer 2 or layer 3. They may or may not be participating in our routing domain by redistributing our routes through their network, and as it is in the case of MPLS VPN, layer 3 MPLS VPN specifically. But in any event, a service provider managed VPN is a VPN that the service provider is involved in, and they manage that network. We don't have really any control over what happens over that network. We're using that network for basic connectivity. There's two ways that we can implement a VPN. We can implement it as a layer 2 VPN solution, where basically the cloud looks like a big switch, and the service provider is providing services over that VPN solution by switching our traffic rather than routing our traffic. Or we can implement something called a layer 3 MPLS VPN, where the service provider actually participates in the routing of the customer's routes. So we have peering relationships between something called the PE router, which is the provider edge router, and the CE router, which is the customer edge router. The customer routes that get received on those PE routers get redistributed through something called an MPBGP link between the PE routers. We have things like VRF, virtual route forwarding instances. There is a discussion of VRF Lite, although VRF Lite is essentially just VRFs without MPLS. So it's not related to this discussion, but VRFs allow us to segregate and separate customer routes to make sure that customer routes maintain a uniqueness and we don't have any overlapping customer routes within our domain. All right. We'll talk about a little bit about the difference between these two. In a layer 2 MPLS VPN, we have a couple of different options. We have something called a virtual private wired service, and then we have something called virtual private LAN service. A wired service is going to simulate a layer 2 point-to-point connection, where you basically have two routers that are virtually connected directly to each other. And a VPLS, which is another layer 2 MPLS solution, is more of a traditional switching based solution where the network basically looks like a broadcast domain, and we can have multiple endpoints participating in the network from that perspective. Now, like I said, you certainly have the capability, or we certainly have enough to talk about where we could talk about MPLS for a day, but that's not really the point of this class. There's other classes that Cisco provides that are service provider based classes that really get into these technologies in a lot more detail. The main concern is that you just understand these general concepts, all right? And that's what our focus is going to be in this case. With regard to tunneling VPNs, which we would really describe as what we call enterprise managed VPNs. Enterprise managed means that you have complete control over how those VPN endpoints are configured, what traffic gets routed over those VPNs, and so on. These are typically going to be VPNs that you're going to run over a public domain, like the internet. We have GRE, we have IPsec, and we have DMVPN. GRE is an encapsulation protocol. It doesn't provide any confidentiality. It doesn't provide any integrity. It doesn't even provide any authentication, but it allows us to encapsulate some packets inside of GRE packets so that we can transport those packets over a public domain. So as a protocol itself, it doesn't really provide all of the necessary functionality that we require to provide message integrity and confidentiality, but it does give us that point-to-point or pseudo point-to-point connectivity. IPsec, which is a whole nother, framework, I guess in this case. GRE is a protocol, DMVPN is a suite of protocols, but IPsec is not really a protocol. It is actually a suite of protocols. It's a framework of protocols that allows us to provide things like confidentiality in the form of encryption with DES, triple DES, AES, etc. Message integrity with MD5 and SHA. Authentication with either pre-shared key authentication or some sort of asymmetric PKI cryptography based authentication. Key exchange protocols like Diffie-Hellman and so on. So it's actually a whole suite of protocols that provides us the capability of tunneling traffic over a public domain. And then finally, DMVPN. Dynamic multipoint VPN provides traditionally hub and spoke. There are several phases of DMVPN. We'll talk about the differences between the phases in a little bit, but provides the ability to create, to take a combination of a couple of these protocols, because that's essentially what DMVPN is. It is a combination of GRE and IPsec. And then with the addition of NHRP, the next top resolution protocol, we can provide this point to multipoint or hub and spoke environment, or we can even do spoke to spoke communication if I'm doing some more modern DMVPN implementations. A hybrid VPN is where you might take a service provider managed VPN and then overlay on top of that some sort of enterprise managed VPN. So maybe running a DMVPN, MPLS over a DMVPN, or an MPLS a network over GRE or something like that. That's what we consider a hybrid protocol. So there are some considerations when we're talking about each of these different types of protocols, and we'll get into some details here. Let's start by talking about MPLS.
Hey, Scott, real quick.
Yes, sir.
If I do DMVPN over L3 MPLS, is that considered hybrid then?
Yes, it is, because you're combining service provider managed functionality with enterprise managed functionality, and that's really by definition what a hybrid VPN solution looks like. Okay.
Right. So so from a financial industry, you've been around the block a few times, right?
Oh yeah.
So is it common for that to be deployed in a financial industry?
It is. It's very common in a financial industry. It's very common in any industry that requires a high level of integrity and confidentiality. We see it a lot in the Department of Defense and DoD contract networks and so on. It's a pretty common scenario because MPLS by itself natively does not provide encryption. So, you know, yes, it is a virtually private network in the sense that your traffic is logically separated from other customers' traffic, but it still doesn't provide for message integrity, it doesn't provide for authentication, and it doesn't provide for confidentiality. So deploying an enterprise managed tunneling VPN solution over a service provider managed VPN solution is very common. All right. So let's talk about MPLS. MPLS, the multi-protocol, label switching. It is essentially a way that we can carry data, and it directs data from one node in the network to the next node in the network based on something called short path labels rather than long network addresses. Now, this is somewhat of the challenge when it comes to talking about MPLS, because a lot of times let me see if I can find a diagram that describes this layer 3 MPLS VPN architecture. A lot of times people are talking about, well, we're running MPLS or whatever, but the reality is MPLS is just a small part of the overall communication process in a layer 3 MPLS VPN. Let me see if I can find a diagram that would be adequate for the discussion that I'm going to provide you here. Yeah, this one probably will work. It's not the highest resolution diagram, but it should suffice for what we're trying to accomplish. So MPLS actually only works in the very, very core of the network. So let me define a couple of these terms before we get into the specifics of MPLS, because I think they're important. CE stands for customer edge. All right. Now they're saying switches in this case, but it could be a router as well. Customer edge. PE is provider edge. P is provider. LDP is a label distribution protocol. MPBGP is multi-protocol BGP, and so on. So here's essentially how a layer 3 MPLS VPN works. I have VPN A over here, VPN A over on the right. Well, obviously my goal in this case is to be able to have network layer reachability between those locations. I want to be able to route from this network over to this network and vice versa without using static routes. So I'm going to use a dynamic routing protocol, etc. So you've got your IGP, which could be OSPF, it could be EIGRP, whatever, that you're running inside your network. You've got a customer edge router that's running multiple protocols. It's running the IGP, and then it's running a peering protocol with the service provider, which is typically going to be BGP, because that's what the service providers understand, but doesn't have to be BGP. It could be EIGRP, it could be OSPF. But the link here between the CE router and this PE router, that's a different protocol typically than what you're running inside your network. Now the purpose of running this connection here is to take routes from your core network, redistribute them into this PE to CE routing protocol so that the PE router can then learn that information at the edge. There's no MPLS running here. MPLS is non-existent at this point. All right? The problem is VPN A might be customer A and VPN B might be customer B. So what's going to end up happening is, or potentially could happen, is that VPN A and VPN B are using the same prefixes, which means now we have a problem. How do I distinguish between customer A and customer B? Because they might be both using the 10 prefixes. Well, what happens is in this PE router, we're running a protocol called MPBGP, multi-protocol BGP. with something called VRFs, or virtual route forwarders. Every customer gets something assigned to them called an RD. That stands for route distinguisher. That route distinguisher gets prepended to the routes that are learned by the customer, which then goes into the VRF. So this PE router has a VRF for customer A, it has a VRF for customer B, and it has a global VRF for the backbone. So we have 3 different routing instances in this PE router. Inside the core, between the PE routers and the P routers, we're running some sort of core IGP, most likely something like ISIS inside the core. But remember, MPLS is not a routing protocol. It's a switching protocol. It's actually kind of a mix between routing and switching. It actually sits at layer 2.5. But MPLS is not even running on the PE routers. Actually, let me rephrase that. It could be, because the labels could be imposed on the PE router, but usually it's not running on the egress on the PE router, because we do something called penultimate hop popping, or PHP, where the labels get popped off before we get to the PE router on the other side. All right. Now again, without getting into the nitty-gritty here, the core IGP and MPLS is running between the PE routers to make sure that we switch traffic through the cloud as quickly as possible. But the dissemination of routing information, customers' routes, only happens between the PE routers. You see this little arrow right here. It's a little bit misleading because it's connected to this arrow here, but actually this is a separate arrow. There is a BGP peering relationship from this PE router to this PE router. And that's actually how the routes are being exchanged. Now that peering relationship is being established over the core IGP, and then the actual routing is taking place with MPLS. But the actual BGP sessions, these P routers are not running BGP. Only the PE routers are running BGP. So the routes get imported here from the CE routers. They get redistributed over to the PE routers through BGP. BGP peers are virtual, they're not physical. All right. Unlike your core IGPs, which are require physical relationships for neighborships. And then finally, the routes are extracted from the VRS and then sent into the CE router using some sort of PE to CE routing protocol on the other side. Okay?
Hey, Scott.
Yes.
Yeah, so the CE, it says you can use OSPF. We do BGP. What is the most common way you see it done?
The most common method that I see between the PE and the CE is BGP. And it's not because BGP does a better job, because it's actually not a full-blown implementation of BGP. You're not even using public ASs in this case. It's just a protocol that the providers understand. And I mean, not to say that they don't understand OSPF, but it is a protocol that is supposed to technically interconnect external ASs, and that's what we're doing in this case. But I've seen MPLS implementations where they use EIGRP between the provider edge and the customer edge. It just depends on, and usually the provider is the one that's going to determine that, but it just depends on what the provider decides to do. Okay?
So it would be far less complex if I did OSPF, right? Because then I would have to distribute from OSPF.
Well, yes and no. I mean, if your goal, you don't really want the PE router participating in your routing domain. It's a security risk. I mean, if you're running authentication in your routing domain, then all of a sudden now you either have to circumvent authentication on that link, or so we usually like to have some demarcation point between what's internal versus what's external. So even in the case of if you were able to run OSPF, if the provider allowed you to run OSPF on the PE to CE link, you probably would still have a separate OSPF process, and you'd redistribute between those OSPF processes, because you just want to have that demarcation point that distinguishes public versus private. It's a very important concept in network security. Technically, you don't have to do that, If the provider edge says, yeah, we'll support OSPF, you can make them part of your routing domain. And yeah, that would make your life a little bit simpler, but then there's no demarcation point to apply security policies or filtering or anything else that you want to apply. At least not, I mean, you can do distribute lists and stuff like that, but again, it's just better to have that demarcation point, okay? So MPLS, which is, you know, somebody says, well, we have an MPLS backbone. The reality is it's a whole bunch of different things happening. You've got your core IGP, you've got your PE to CE IGP or protocol, you've got your service provider core IGP. IGP is interior gateway protocol, internal routing protocol. You got your MPLS core, you got your label distribution protocol, you got MPBGP. There's just a lot of things happening in this type of environment, all right? So MPLS is really technically just a small piece of the overall picture, all right? Now, the nice thing about MPLS, the name itself implies the capability. MPLS stands for multi-protocol. So you can do T1s, you can do ATM, you can do frame relay, you can even do DSL. And here's the reason why. MPLS is a layer 2.5 protocol. It's the only protocol that doesn't fall into the category of a specific OSI layer. It's not a switching protocol, it's not a routing protocol, it kind of sits in between. All right. So it is a scalable, it's protocol independent, means it runs over any layer 2 protocol. In the case of the actual MPLS core, the MPLS packets are assigned labels. Then packet forwarding decisions are going to be made solely based on the contents of those labels. So there's no need to examine the packet itself. This gives us essentially an end-to-end circuit across any type of transport medium using MPLS. What we're trying to do is we're trying to eliminate the dependence on a particular data link layer technology like ATM, like frame relay, like SONET, like Ethernet, and so on. We're also trying to eliminate the need for multiple layer 2 networks to meet the needs of different types of traffic as well. MPLS does that, all right? Like I said, MPLS kind of operates generally somewhere between traditional layer 2, the data link layer, and the network layer. So it's one of the only protocols that is considered to be a layer 2.5 protocol. And we can talk about the different types of MPLS deployments. I can give you a couple of definitions, but again, it's not really the point of this class. I'm going to go into a little more detail because I do think it's important to understand some of the terminology. But the reality is, from a functionality standpoint, unless you guys actually go and work with a service provider where you're actually establishing these VPNs, it's really not necessary to understand the specifics, right, of how this label switching works and whatnot. If you go into the CCNP, yeah, go ahead.
Well, from our point of view, I mean, at least from my point of view, MPLS, it's a black box. The provider gives us, we advertise our routes to them. We do DMVP and protocols over their network. But I don't work for an ISP. I'm not too concerned about the internals of the MPLS switching.
Right. Exactly. Yeah. And I agree. I agree completely. So what I'm going to do, instead of going into the specifics, I'm just going to define a couple of the characteristics. We'll talk about an MPLS label, what the format of the label is, and that's important for the purposes of QoS. Because you do often want to run QoS over these internet these service provider backbones. So we'll talk about that, and we'll talk about what a label switch router is, what a label edge router is, and so on. So, and then we'll just move on to the next topic. But MPLS works by essentially prefixing packets with an MPLS header. That MPLS header contains a 20-byte label value and a 3-bit traffic class field, which we call the 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 TC bits, traffic classification, which are used for QoS. So we have, it's now called the traffic class field. It used to be called the experimental field, EXP field, but now it's called the quality of service / ECN field. So we have at least 8 classifications of traffic that we can apply over an MPLS backbone because of that 3-bit field. 000 to 111, which is a decimal value of 0 to 7. Then we have a 1-bit bottom of the stack flag, and then we have an 8-bit time to live field. So MPLS has its own TTL value, which is essentially represented the same way that the time to live is used in a packet, a routed packet. Okay. So we have a label switch router, which is just a transit router within the service provider backbone that's switching labels. So we have an ingress label and we have an egress label, so we're switching those labels. We have a label edge router, which operates at the edge of the MPLS network. It either pushes a label onto an incoming packet or it pops the label off of the outgoing packet. And then we also have this concept called penultimate hop popping, PHP, which allows us to actually remove the label even before it gets to the label edge router at the on the egress side. We have provider edge routers, we have provider routers, we have a protocol called the label distribution protocol, which allows us to exchange the labels between the routers themselves. And then we have our label switched paths. All right. So there's a swap operation, there's a push operation, there's a pop operation. As the packets enter the MPLS network, we're doing a push operation. As the packet transits through the MPLS backbone, we're doing a swap operation. And then as the packet leaves the MPLS portion of the network, we're doing a pop operation. All right. MPLS does support multicast. I mean, multicast was for the most part an afterthought in MPLS. And it's obviously multicast has become kind of a really important component in enterprise and service provider managed VPNs. So after RFC 4875, I believe it was, huge surge in the interest of deploying MPLS multicast and so on. So we've seen kind of a lot of that taking place. But that's the extent of what I'm going to say about MPLS. Let me just describe real quick what we're looking at in this slide here. That topology that I showed you guys, this topology right here represents the bottom diagram, where the service provider's backbone is essentially is participating in routing, and that's why we have a big router. The top diagram describes a switched MPLS solution, which there's 2 options. You have BPLS, virtually private LAN service, or you have VPWS, virtual private wired service. In either case, the routers look like they're connected either through a single point-to-point Ethernet connection or through some sort of broadcast domain functionality, like a switch in the middle. And that allows us to do things like run VLANs over these networks, and we can use layer 2 services between the routers if we want to use layer 2 services and so on. From the customer's perspective, whether you decide to choose a layer 3 MPLS VPN or layer 2 depends on what your overall objective is. All right. If you want to manage all of your own routing information and you want to make sure that you're disseminating your routing information and there aren't any other VPNs that you want to participate in from a routing perspective, then you simply implement a layer 2 MPLS VPN. All right. If you want to allow yourself to participate in multiple VPNs, in other words, maybe an internet-based VPN, maybe a service provider managed telephony VPN where they're hosting your telephony services for you, and then you got your corporate VPN. You know, if you're going to participate in several different VPNs, you may choose to use a layer 3 MPLS VPN, where you want to outsource your routing to the service provider. The service provider is then going to maintain that domain for you. Does that make sense? So it just depends on the environment. I would say most commonly we see, well, you know, I'm actually thinking about whether or not I should say that. I was going to say the most common we see is a layer 3 MPLS VPN, but we have several customers that are running layer 2 MPLS VPNs as well. So, all right. The next thing we'll talk about in this lesson here is GRE. Now, GRE stands for Generic Route Encapsulation. It is a tunneling protocol. It was developed by Cisco to encapsulate just about any kind of protocol inside a virtual point-to-point link over any kind of IP network. Traditionally, it's going to be the internet, but it could be a private network as well. We may decide to encapsulate data over a private network. All right? So the purpose of this protocol is to act as a tunneling protocol. It was, like I said, developed. It was actually introduced by Cisco quite some time ago. In 1994, it was there was an initial RFC that was issued, RFC 1701, and then there was an addendum to that, 1702, and then finally a major change in 2784. But the GRE works essentially at layer 3. It's an encapsulation protocol at layer 3. We have a GRE header. This is defined in RFC 2784. It includes several different fields. We don't really need to get into the specifics, but GRE is protocol 47. By the way, when they say protocol, they're referencing the protocol field within the IP header. So whenever you see a protocol specified, you know that it is a layer 3 protocol. ICMP, for example, is protocol number 1. EIGRP is protocol 88. OSPF is protocol 89. Whereas RIP doesn't have a protocol because it runs on top of UDP. BGP does not have a protocol because it runs on top of TCP. So anytime you see a protocol ID, that indicates that this is a protocol that's encapsulated inside of IP directly. There isn't a transport layer function. All right. So the GRE header, standard GRE packet header, has 3 bits that are used for like a checksum bit, a keying bit, whether or not a key is included, a sequence number bit, and then we have some reserved bits as well. We have a version field. We have a protocol type. So this could either mean like IPv4 or IPv6. Basically, what am I encapsulating inside of GRE? There's a checksum field. There's a key field that contains things like application-specific key values, and then we have a sequence number and so on. So keep in mind, obviously, if we are encapsulating datagrams inside of GRE, that there's overhead associated to this. All right, and specifically in the case of GRE, well, the GRE header itself is 24 bytes. So keep that in mind if you're dealing with MTU issues. If you're encapsulating packets inside of GRE, you need to account for that 24 bytes of overhead. And that doesn't include other things you might be doing in conjunction with GRE, which includes things like IPsec encryption and so on. Okay? All right, so the passenger protocol or encapsulated protocol could be IPv4, it could be IPv6. The carrier protocol itself is GRE, and the transport protocol is IP. All right. Like I said, there's a protocol type field in the GRE header to support the encapsulation of any OSI layer 3 protocol. If you come out to Google here, we love Google. I don't know how we got away with not using it before, but and I just search for protocol ID values. All right. Sure enough, it's the IANA. Again, those guys are responsible for anything that has to do with numbers. And we can see all the different protocols. ICMP is protocol 1, IGMP is protocol 2, IPv4 is protocol number 4. And by the way, those aren't the hexadecimal representations. In the case of the hexadecimal values, are completely different numbers. I was going to see if there was a reference to the hexadecimal equivalents, because IPv4 is actually is hex 800. But in the case of protocol ID, from the perspective of a packet, right, it's number 4. So for example, if I take a look at down here at 88, you'll see that that is EIGRP. Right, OSPF is 89, MTP, multicast transport is 92, and so on. But essentially, because that GRE protocol field exists, I can put any of this stuff inside a GRE and send it over. We're just traditionally used to using GRE to encapsulate routing protocols. GRE is a stateless protocol, which makes sense. It operates at layer 3, and every protocol that operates at layer 3 is stateless. So there's no flow control, there's no sequencing and acknowledgments. It doesn't include any encryption, doesn't include any authentication. 24 bytes of overhead, like I mentioned before. All right. So essentially what is the point of GRE then? Well, if you look at the diagram here, I want this router on the left to be a peer to this router on the right. Literally neighbors, OSPF neighbors, EIGRP neighbors. The problem is I have this big dark cloud in the middle, which represents the internet. All right. Why is that a problem? Well,
because if you want to run a routing protocol such as EIGRP, which uses multicast, you're going to have a problem.
Right, because multicast doesn't work over the internet. And also, in general, the internet is, well, first of all, routers, in order for them to become neighbors, have to be in the same common subnet. Obviously, two routers connected to the internet are not going to be in a common subnet, on the WAN side anyway. So lots and lots of reasons why I can't form a neighbor relationship over the internet, like you said, because multicast is not going to be supported. And they're just not in a common subnet, which means I can't form neighbor relationships anyway. So the EIGRP packets or the OSPF packets end up being essentially the passenger protocol in the case of GRE. All right. But still, a consideration to take into account is that GRE does not include any kind of confidentiality or security. So then we start to talk about implementing some sort of tunneling protocol on top of that in the form of some sort of VPN solution. All right. DMVPN, Dynamic Multipoint Virtual Private Networking. It's a tunneling protocol. It's a form of VPN that is, I would say, originally was a Cisco iOS type function, but it's also supported on other types of routers and firewalls today. But the benefit of a DMVPN is that it provides us the capability for creating a dynamic mesh of VPN endpoints. And the dynamic piece is really the most important piece that we're talking about here. All right, that is absolutely the most important piece, is the dynamic nature. Spokes don't have to be statically configured. They can be dynamically configured, and we'll talk about that in a second. All right. The only thing that you have to pre-configure is the hub router. All right, and all the spoke routers basically just call home, register themselves with the hub router so they can have dynamically addressed endpoints. We don't have to use static addressing, and spoke deployments become a lot simpler because they just simply phone home, so to speak, and create this tunnel. But on top of this, and this is the most important part, we include IPsec, the IP protocol suite, IP security protocol suite, and we include ISAK-AMP, which is what we call the Internet Security Association and Key Management Protocol. And both of these are just fancy terms for describing the ability to add security on top of this virtually private network through the use of VPN technologies and so on. DMVPN was actually initially configured traditionally to build hub and spoke networks. You would statically configure the hub, which is your VPN head end, on the spokes. No change in the configuration on the hub is required when you're adding new spokes because you're basically just statically configuring those spokes to communicate to the hub. The problem with using this initial design, this initial hub and spoke network design, is that the tunnels between the spokes, we couldn't have tunnels dynamically created between the spokes, and all the communication had to go through the hub in order to support the communication from spoke to spoke. With newer implementations of DMVPN, we now have what we call dynamic mesh, or on-demand spoke-to-spoke communication that can be facilitated without the configuration of additional VPN endpoints or VPN configurations. All right. So we don't have a heavy load on the hub. The hub doesn't have to be a transit router for all the traffic going from spoke to spoke, and then we can route traffic directly from one spoke to the other. So when it comes to DMVPN, there are actually 4 technology components that exist. Number one, you've got your GRE, all right? Or if you're running a modern DMVPN solution, what we call MGRE or Multipoint GRE, to do spoke-to-spoke tunnels, tunnel creation. That was RC 1701, like I said, but there was 1702 and 2783 or whatever it was that I mentioned previously. And then we have NHRP, the Next Hop Resolution Protocol. RFC 2332, NHRP was actually used to allow this dynamic creation. Number one, the registration of the spokes to the hub, but number two, the ability to dynamically resolve spokes from other spokes and be able to, and so that you can route traffic from spoke to spoke directly without having to go through the hub. And then on top of that, we throw in IPsec, which can either include encryption or authentication or both. Typically, it's going to include both. And then finally, we have our routing protocol, EIGRP, OSPF, RIP, BGP, on-demand routing if it's necessary, and so on. All right. EIGRP and BGP allow for a lot more spokes per hub, but there are also downsides to running those two protocols as our internal routing protocol. Just like with GRE tunnels, DMVPN gives you lots and lots of different options for doing encryption, including none. You don't have to run encryption with DMVPN. Most people do. Obviously, in the case of encryption, our advanced encryption standard is what we generally recommend as a standard. All right. So that's kind of a high-level view of DMVPN. Now let's take a look at some of the benefits of DMVPN. That's on page 41 of your book. And I think I've already kind of mentioned a few of these benefits, but I want to just hit them up one more time. And then we'll take a look at some of these other protocols in depth. So with regard to benefit number one, they say the hub router configuration is reduced. And that is because we use something called MGRE or Multipoint GRE. We create a generic GRE interface without specific configurations. And then as each spoke calls home and registers to the hub, it spawns off a configuration for a specific tunnel interface for that particular spoke router. But it does it dynamically, all right? Now, and it does it logically. It doesn't do it physically. So the size of the configuration of the hub router doesn't grow We can have 100 spoke routers, we can have 500 spoke routers, and in every case that multi-point GRE interface is being used to logically create all of these connections to these spoke routers. Automatic IPsec, we use NHRP for resolution of the peer destination addresses, and then the peer destination addresses are our publicly routable addresses. And then by knowing those publicly routable addresses, I can then go through the process of establishing an IPsec tunnel from point to point on those endpoints. And then we have the ability to have dynamically addressed spokes. Because the spoke routers simply call home, right? They don't, they're not required they're not required to be statically configured on the hub. The spoke routers simply call home. Then we don't care about what the IP address of the spoke router is. All we simply have to do is go into the spoke router and apply a configuration on the spoke to point it to the hub. And then the spoke router calls home, announces itself to the hub. You know, there's some basic authentication, and then the DMVPN session is established. All right? And that's really what MGRE provides us the capability of doing. All right? MGRE stands for Multipoint GRE. If my goal on the left diagram here, you see the traditional hub and spoke GRE implementation, DMVPN implementation. On the right side, we see more of a modern DMVPN implementation where we're actually allowing spoke-to-spoke communication. Well, obviously, if I'm going to establish more than one tunnel between multiple endpoints, I'm going to have a multi-point GRE interface. You only have to have one tunnel interface configured on the router, and you can have as many multi-point GRE peers that you want. I mean, theoretically, obviously not physically, but theoretically. So we can have lots and lots of spoke routers, we can have spoke-to-spoke communication, and so on. It's very important to understand, though, in order for a router to learn the IP address of other peers, we have to use some sort of dynamic protocol to map out those addresses. It's a chicken or the egg thing, right? I can use routing protocols to map out networks, but I can't send routing protocols over the network until I have a network established. So in that sense, we have to have another protocol that provides that functionality, and that's what NHRP does. All right? The last bullet point on page 42 is really important. MGRE interfaces also support unicast, multicast, and broadcast traffic, and that's really the one of the main reasons why MGRE would be utilized as a primary protocol. All right? All right. Let's talk about the next hop resolution protocol, because this is a key component to this GRE solution, this next hop resolution protocol. It's an extension of actually something that comes from ATM ARP actually. And the idea here is that we're going to be able to use this particular protocol. A sender specifically would use this protocol to determine a route with the fewest hops to whatever receiver it's trying to communicate. All right. Now it is different than, say, an ARP type protocol, where in an ARP type protocol we're kind of allowing routing optimization across multiple subnets. NHRP is implemented in order for us to be able to define the next hop servers across an IP subnet. In other words, I'm trying to discover who is the destination for this particular traffic. There's two different types of addresses that come into play when we're dealing with GRE. You've got a public address, which is the address that's on your physical interface that connects to the public domain, and then you have something called a tunnel interface address, which is usually a private address that is tied into your GRE backbone. All right? So based on RFC 2332, which is what defined NHRP, we have a host or a router that wants to communicate over this network. It needs to determine that layer, that IP address that defines essentially the next hop towards the destination. That's what NHRP does for us. All right. So taking a look at this diagram here, it is a client-server-based protocol. The hub, obviously, in this case, is going to act as the server. The spoke routers, in this case, are going to act as the client. So let's say, for example, the router on the left here. All right. The first thing that's going to happen is all five of these routers are going to have to register themselves to the NHRP server. And that's done through the traditional DMVPN communication process. The spoke router calls home to the hub router. In that process, the hub router has been able to identify not only that the spoke router exists, but what is the public address of the interface of that router, and then also what is the tunnel address of the tunnel, what is the IP address of the tunnel interface of that particular router. So the 209.165.200.226 address that you see there, that is the physical address. And then the 10.112 and the 10.113, those are the tunnel addresses. And there's always a mapping, right? The tunnel is the transport, the public address is the transport. The tunnel is the encapsulation protocol that allows us to encapsulate, the traffic that needs to be routed. All right. So router on the left says, "Hey, I'm 209.165.200.228, and by the way, my GRE tunnel interface address is 10.112." The client on the right registers and says, "Hey, I'm 209.165.202.149, and my tunnel interface is 10.113." And as you can see, there's an NHRP database on the core router, on the hub router, that maintains a list of all this information. All right. So let's move on to the next step. In the next step, the router on the left says, "Hey, I need to send traffic to 10.113." And by the way, that information was exchanged through my routing protocol. Remember, 10.113 is logically the next hop for this GRE traffic. It's not the physical IP address on the device, it's the logical address on the device. So there are some routes that are being advertised by the clients which are mapped to next hop addresses. In this particular case, there's some sort of subnet behind this router here, and this router knows based on its routing table, hey, if I want to get to that subnet behind this router here, I need to send the packet to 10.113. Now in traditional GRE and traditional DMVPN, the traffic just simply goes up to the hub, and then the hub forwards the traffic down to the other client. And then in a different phase of DMVPN, the first packet goes up to the hub, then the hub sends a redirect message back to the source. It says, "Hey, by the way, you need to stop sending me this traffic, you need to send it over here." So that's another option. And then the third option is to use NHRP, where I send an NHRP query. This arrow is kind of in the wrong direction, but I send an NHRP query to the hub saying, "Where is 10.113?" And the hub router responds with, "Well, 10.113 is at 209.165.202.149. And using its multipoint GRE interface, we then establish a spoke-to-spoke GRE tunnel with encryption and all the bells and whistles, and then we start routing traffic directly from spoke to spoke. Make sense? All right. Another option that we have, and by the way, that's literally it with regard to DMVPN, even though, again, we could spend a half a day or a better part of a day talking about DMVPN. Believe it or not, in this particular version of the course, we don't even configure DMVPN. So,
Scott?
Yes, sir.
Before we move on from DMVPN, I have a little real life scenario. If you want to.
Sure, go ahead. Yeah.
So we recently implemented DMVPN. We had a requirement of putting encryption on all our MPL sites.
Okay.
So we decided our best solution, instead of doing traditional static VPN, IPsec tunnels, to implement DMVPN. It's GRE, Multipoint GRE with obviously IPsec on top of that.
Yep.
Worked okay. Worked great. Not issue, but some of the things we ran into is we initially tried to run it with OSPF as the overlay routing protocol. We're running BGP, layer 3 BGP with the provider underneath the underlay. So we decided to go OSPF on the overlay, and we had some issues, I think mainly due to our redistributing we're doing with the head-end routers, the MPLS head-end routers, and our environment's very complex. We're running pretty much every, all three routing protocols, BGP,
sure.
OSPF, and EIGRP. So we had some redistribute issues and failover. So we decided to go. We did implement that at one site. It wasn't failover like we wanted, so we went with EIGRP. Now I know Cisco recommends EIGRP in that environment, and I think it's, from what I read, it's mostly from scalability, not configuration. But just as a general, I just want to hear your opinion. Like, what routing protocol, overlay routing protocol, would you like or recommend in a DMVPN environment over MPLS?
So it's a great question, and I am going to go with what Cisco states, and I'll explain why. EIGRP is more suitable for that type of environment because it operates in a flat architecture. Everything is in one autonomous system. And the complexity of design gets eliminated because there is no complexity, right? You don't have a hierarchy where you have, like with OSPF, where you have backbone areas and non-backbone areas and so on. You don't have to deal with the different network types that OSPF has to deal with, and ensuring that the appropriate network types are selected or either manually configured. And just overall, EIGRP scales better and it's more suitable in that particular type of environment because of the dynamic nature of DMVPN. Whereas in OSPF, you have to follow a specific design architecture. You have to define what's your backbone area. You have to define what are your non-backbone areas. And there are very specific requirements on what types of routers can communicate to what types of routers. Now, that being said, you could logically deploy OSPF as a flat architecture by simply using one single area. Just put everything in area 0 and call it a day. And then in that sense, it kind of becomes the same as EIGRP. But with the amount of overhead and then the limitation of running a single area OSPF design. For example, there's no way to do summarization in a single area OSPF design because you can only summarize on ABRs. So you lose that flexibility, and with the lack of summarization comes the lack of scalability. Does that make sense? So that's the reason primarily why EIGRP is recommended as a protocol, because you can summarize anywhere. It operates in a flat architecture. It's not that EIGRP is more scalable than OSPF, because it definitely is not. But in this case of implementing it in a DMVPN, because of the nature of spoke-to-spoke and hub and spoke communication, it's just a much better suited protocol, more suited protocol for that environment. You can make OSPF work, and we do have clients that run OSPF over a DMVPN, but very, very strict design elements to that. Very, very strict design elements.
I think that's what configuration was very complex. Our network's already probably over complex on top of it.
Exactly.
And we did roll it out to one location, and just rolling out to a second location, we saw some transient traffic, and the complexity of it was becoming a nightmare. And so we just have to just roll. Even though we're sort of an OSPF shop now, because of the Palos that Jason mentioned earlier, but we decided to do EIGRP for the overlay for the network. So I think I made the right decision on that. So
you definitely did. You definitely did. Again, you can do OSPF. It's not that OSPF doesn't work. It's just the requirements are just so much more specific. All right. Now with yeah, no problem. You're no problem. IPsec is a framework of protocols, and really the easiest way to kind of define IPsec is just to simply take a look at, what that framework looks like, and it's a building block of a whole suite of protocols. Actually, let me do IPsec framework so I can pull up the diagram I want to show you guys. It really just kind of shows us all of these different protocols that are involved in this process. Let's see. I guess that one's okay. This is pretty much the same diagram. And colors are a little bit different, but that's all right. So this is what the IPsec framework looks like. Now you have choices in how you decide that you want to implement the protocol. You can do something called AH, which stands for Authentication Header, which means essentially that you're just implementing authentication without encryption. So you can see the confidentiality block is missing, but you still have message integrity, you still have authentication, you still have some sort of key exchange process. Or you can choose to run ESP, which includes any one of these different encryption processes. Typically, it's going to be the advanced encryption standard. ESP stands for encapsulated security payload, which essentially is encryption. Or you can do both. All right. Cisco doesn't really support the use of just authentication. So you're most likely going to see both in that case. All right. But this is what I mean by a framework of protocols. You can choose what you want. Stick it in the little box here for confidentiality. You can choose what you want for message integrity. You can choose what you want for authentication, whether it's pre-shared key or RSA stands for Rivas, Shamir, and Edelman, but it's basically PKI, public key infrastructure, digital certificates. DSA probably is another box that should be here. And then there are very different flavors of SHA as well. And then we have our key exchange process, right? Diffie-Hellman and ECDH is probably something that should be listed here as well. Elliptical curve, Diffie-Hellman. But the IPsec framework is just a bunch of building blocks that you can put together to provide things like encryption, confidentiality, message integrity through some sort of hashing process, authentication through some pre-shared key authentication process, or public key infrastructure authentication, and so on. All right. So that concludes that lesson. All right. We're going to go ahead and move right in to the last lesson for today, most likely, which is the final lesson in this module, which is lesson 4. And this is where we're finally going to get into an exercise and take a look at a configuration. All right. So we'll see you guys in the next lesson.